Quiz 2 is due today. Make sure you give me that before you leave. We're going to start today's class with a little hint about the Gamma project. So 2 of the questions in the Gamma project have to do with the stuff we talked about last class, proving that an integral converges or diverges. So I thought that I would help you with them a little bit. Particularly number 8, it's difficult, but we'll do number 5 first. Okay, I want to explain why gamma of 1/2 converges. So the gamma function, if you haven't started looking at this project yet, is defined by this, right? So gamma of x is equal to this beast of an integral. And x is just a number, right? X is the input, so you plug in some number, and that means everywhere you see an x in the formula, replace it with that number. Right? So it works just like normal functions do, even though there's an integral there. So gamma of 1/2 means replace the x in that formula with a 1/2. So this is going to be the integral from 0 to infinity of e to the negative t times t to the 1/2 minus 1, right? And that would be negative 1/2 dt. So gamma of 1/2 is the value of this integral. It's the area under this curve, that e to the negative t times t to the negative 1/2 from 0 to infinity. So we're trying to prove that the area under this curve is finite, that this thing converges. So if we're going to use a comparison test, then we have to break this into 2 separate integrals, because we know stuff about integrals from 0 to 1, and we know stuff about integrals from 1 to infinity. That's what we discussed last class. So I have to show that both of them converge to show that this is a finite value from 0 to infinity. So this whole thing is finite. If I break it into a sum of 2 integrals, both have to be finite. All right, so I'm going to rewrite this as the integral from 0 to 1. And just to help me visualize the size of the integrand, I'm going to rewrite this as 1 over e to the t times t to the 1/2. Right, so I moved those 2 things into the denominator and made the exponents positive, dt. And then I'm going to add to that the integral from 1 to infinity of the same integrand, 1 over e to the t times t to the 1/2 dt. Morning. Yep. Okay, so I have to look at each of these integrals separately and prove that they are both convergent. So if I use a comparison test, we'll look at this guy and this guy separately. So I'm going to compare my integrand, 1 over e to the t times t to the 1/2. We'll look at this one first. 1 over e to the t times t to the 1/2. All right, so I'm trying to prove that this converges, right? So I need to show that that integrand is smaller than something else that we already know converges. Okay, so what could we compare it to that we know already converges, and my integrand, this guy, is smaller than it? Yeah. Yeah, 1 over e to the t in this case. This function, my integrand, is always smaller than 1 over e to the t, right? Because the denominator will be bigger. Because I'm going from 1 to infinity, e to the t and t to the 1/2 are both increasing functions. So as I go from 1 to infinity, both of these factors are getting bigger, which means that the product of the 2 is going to be bigger than just one of them. Okay, so this denominator, e to the t times t to the 1/2, is bigger than just e to the t, which means this whole fraction is smaller. Bigger denominator, smaller fraction. Okay, and we know that this guy converges. Okay, so I know e to the t converges. I know that this guy is always smaller than something that converges. So this has to converge. So you should really write a sentence explaining. I'm out of room. Right, so this is smaller than a convergent integral, so also converges. Does that make sense? Okay, so we've got the first piece. Now the other piece, from 0 to 1, remember the rules flip now, right? Now if you compare, so from 1 to infinity, when you compare to 1 over x to the p, when p was bigger than 1, it converged, and less than 1, it diverges. It's the opposite when you're looking at 0 to 1, right? When p is bigger than 1, it diverges. Less than 1 converges. So I want to compare 1 over e to the t times t to the 1/2. I need to show that this is always less than or equal to something that converges on 0 to 1. So what would a function be that converges on 0 to 1 that is always going to be bigger than this guy? I need something that this integrand will be smaller than, always smaller, of something that we know converges on 0 to 1. Would the same comparison work here if I wrote 1 over e to the t? Would that help me? Right, exactly, yeah. So yes, this inequality is true, but this is divergent, right? 1 over e to the t on 0 to the 1 on 0 to 1 is divergent. Okay, so that is not going to help because being less than something that's infinite, you could still be infinite or you could be finite. So that doesn't help. I need something that I know converges. So what else could I use instead of 1 over e to the t? 1 over t to the half. Is this inequality true? Yeah. So this denominator, I'm multiplying two increasing functions together. So when I multiply them, the product is going to be bigger than either of the factors. So this denominator is bigger than this denominator. So this fraction is smaller than this fraction. So this inequality is true. And what about 1 over t to the 1/2? On 0 to 1, it converges. It converges. So then you should write a sentence explaining. Okay, so my integrand is always smaller than the function that converges on 0 to 1. So my integral has to also converge. And let's say you have trouble like coming up, explaining to yourself that these two things, the inequality, right, is difficult. You can always graph your two functions and look on 0 to 1 and see that this one is always below this one. So you can always use your graphing calculator to help confirm these inequalities. So let's put my comparison, my integral for comparison first. We'll have 1 over the square root of x. There's my function for comparison. And then my integrand itself is 1 over e to the x times the square root of x. And this second one I'm going to bold so that I can know which one is which. So I'm looking to see that the bold line is going to be below the non-bold line. I got to choose a good window. Now for x, I want to see what happens on 0 to 1, right? So I'm just going -0.5 to like 1.5. And then for y's, maybe I'll go, I know these things will always be positive. So maybe I'll go 0 to, I don't know, 3. Okay, so that's my comparison. And then there's my actual integrand, which is always smaller than the comparison function. It's always below. So this is a good way to confirm that you've written a correct inequality. You could also just plug in a number between 0 and 1, right? Plug in a half into both sides of this inequality, make sure it's true. For those days when you don't have a graphing calculator with you. All right, so let's look at number 8. Number 8 is the really tricky one. So I'm pretty much just going to tell you how to do it. Gamma of 0. We want to prove that it diverges. So that means I'm going to go back to my original gamma function, like this guy. I'm replacing this x with a 0, which means you have to replace that x with a 0. Just plug in a 0. So we end up with the integral from 0 to infinity of e to the negative t times t to the negative 1 dt. Same approach as the last one. I'm going to break it into two integrals, 0 to 1 and 1 to infinity. And to show that the whole thing is infinite, I have to show that at least one of them is infinite, right? Because something infinite plus something finite is still something infinite. So to show convergence, you have to show they both converge. To show divergence, you just have to show one diverges. All right, so break this into the integral from 0 to 1. And again, I'm going to rewrite this as 1 over t e to the t plus the integral from 1 to infinity of 1 over t e to the t dt. I didn't drop the x, I replaced it with a 0, right? So the function is gamma of x, right? So x is my variable in the gamma function. So when I write gamma of 0, right, just like any function, when you put a number in place of the x in the parentheses, you also replace the x in the formula. Okay, so I'm going to leave this one to you. This one converges. And I'll leave that to you to prove. It's not a difficult one. The hard part of this problem is to show that this first integral diverges. Okay. Okay, so this first one, it's gonna be, we're gonna do this a little bit differently than we have been doing this. I mean, it's not crazy different, but it's tempting to just try to compare this to either 1 over t or 1 over e to the t. Neither one's gonna help you, right? If you compare to 1 over e to the t, you get something that allows you to draw no conclusions, because 1 over e to the t diverges. Being smaller than something divergent doesn't help you make any conclusions. And if you compare to 1 over t, you show that you are smaller than something, yes, smaller than something divergent. So you can't make any conclusions. Oh, and 1 over t converges. You're bigger than something convergent. Doesn't help you draw any conclusions. So whether I compare to 1 over t or 1 over e to the t, I can't make any conclusions. So I'm going to just write that down. So if I compare, right, this guy's divergent, and it turns out that's the inequality. But being smaller than something divergent is no help, right? If we were bigger than something divergent, you could show that it's divergent. And if I compare 1 over t e to the t to 1 over e to the t, this is that's true, right? And what happens to 1 over e to the t on 0, 1? Convergent or divergent? It's divergent on 0 to 1. So again, we're smaller than something divergent. Right? So this is no help either. Right? So proving that you're smaller than something infinite does not prove anything. You can't conclude whether it's infinite or finite. So in both of these cases, we're showing that the integrand is smaller than something infinite. Doesn't help me prove infiniteness or finiteness. So instead, get a new page here. Instead, I'm going to try to sandwich this integral between two other integrals. So okay, I'm going to try to sandwich this between two other integrals. So if I just look at the e to the t and I put in a 0 just into the e to the t part, just make that exponent 0, I get 1 over e times t, 1 over e times t. Okay, so is that bigger or smaller than 1 over t e to the t? Yes, the denominator will be bigger. So if you have e to the 1, right, that's going to be bigger than e to any other value between 0 and 1. So this is going to be bigger than or equal to the integral from 0 to 1 of 1 over t times e. And if I put in a 0 just into the exponent, this becomes 1 over t, right? And this integrand will always be smaller this I already knew, right? This part I already knew, and it was unhelpful. Already knew that, and it wasn't helpful. But this part, right? You might have to think a little bit about why that inequality is true. You could graph them both, plug in some values, just convince yourself that this function is always smaller than this function. And then take a closer look at this integral here. I can pull out a 1 over e. Always less than or equal to my integral of interest. And what do you know about this function on 0 to 1? Integral from 0 to 1 of 1 over t dt. No, because it's not continuous at 0, so you can't use the fundamental theorem. Yeah. but it's 1 over x to the p, right? P is 1. Does it converge or diverge? This diverges. So my integral that I'm actually interested in is bigger than something that's divergent, which means it is also divergent. All right, so that's definitely a tricky one. You really may have to go back and look at this and think about it, but I have given you the trick. Okay, so we're starting chapter 8 today. This chapter is all about applications of the integral. We will look at geometry, physics, economics, probability. When all is said and done, in every application, you're going to be making up a formula sheet full of the myriad different settings in which integrals arise, and you use these formulas competently on the next test. Right? So over the next coming weeks, it may be tempting to just wait for me to give the punchline, to just tell you the formula of the day, how to do it. But I really want to encourage you to focus on understanding why the integral is an appropriate tool in all these seemingly unrelated applications. Formulas come and go, right? If you ever need one in real life, you can just look it up, right? So don't sweat the formulas. Try to strive for the comprehension of where the formulas come from and why we're using that formula. This material tends to get going fast and furious. So try to keep up with the homework and reading as best you can right after each class instead of trying to leave it until do it all at once. Okay, so this whole chapter is built on the idea of slicing. So we're going to quickly revisit Riemann sums. Remember, if you have a continuous function, for now assuming it's positive, and we're looking for an estimate of the area under the curve from A to B, you slice it into rectangles. Okay, so you take your whole interval, you break it into n little subintervals. Then the width of each of those rectangles, width of each interval, is going to be b minus a over n. Take the length of the whole interval and divide it into n equal pieces. And then you can approximate the area under the function by a right-hand sum, right? Where each rectangle is the height of the function times delta t. Height of the function times delta t. And then we find the exact area by letting the number of rectangles go to infinity. So you take this sum and let n go to infinity. And we denote that by a definite integral. The integral from a to b of f of t dt. So it's crucial to understand how the pieces of the first expression, the limit of a sum, become the pieces of an integral. Okay, because we're going to be doing this over and over again. We're going to be adding up, slicing, adding up all the pieces, and then taking a limit, and that's going to make an integral. Okay. So f of ti becomes f of t, delta t becomes dt. The summation symbol, when you take the limit together with the sum, becomes the integral symbol. Right? And then you have to include the bounds of integration, a and b. Okay, so we're going to use this idea of slicing to find some areas and volumes of easy shapes. The basic idea is written out here, and maybe we'll come back after we do one example. Okay, so this is the basic procedure, but don't read it right now. We'll do this first example here. I want to find the areas of these figures by writing a Riemann sum. I'm going to add a sum, and then I'm going to rewrite as a definite integral when I let the number of slices go to infinity. Okay, so this is a triangle. Base 6, height 3, right triangle. I could just use a formula, right? So, but the point is I'm going to start with some easy things. to figure out by slicing, and then that will be able to move that technique onto things that you don't have a formula for. Okay, so I take a representative slice, just a random slice in my triangle, and make a rectangle. And I'm going to call the distance from this point to my rectangle x, and the width of my rectangle delta x. All right, so I need to come up with the area of that little rectangle. Okay, so the area of my little rectangle is going to be delta x times the height of that rectangle. And how could I figure out the height of that rectangle? Proportionality of similar triangles, yeah. So I could use the height at x, right? Using this height to get my rectangle. And I can use similar triangles. So I would say this height, we could call it h, right? For the height of my rectangle. H is to 3 as what is to what? Right, the height of the little one is to the height of the big one as close, not delta x, but x, yeah. X would be the base of my little triangle, 6, the base of the big triangle. And then I would solve this for h, so that I would be able to have only x's in my formula. Okay, so this says that h is x over 2. And then every rectangle is going to have a width of delta x and a height of x over 2, because we're letting this x move, right? That's a variable. So I'm going to sum these all up. I'm going to take a sum of all these rectangles and add them up. Take a sum of delta x times x sub I over 2. So each of these are my x sub i's. And then I'm going to take a limit as n goes to infinity. So this is going to become an integral of x over 2 dx. The delta x becomes a dx. And then what should my bounds of integration be? X is going to go from where to where? Zero to 6. Start at 0 and move to 6. All right, so let's actually finish the antiderivative and plug in. It's a 6, not a b. Okay, so this becomes x squared over 4 when I take the antiderivative, evaluated from 0 to 6. 6 squared is 36, divided by 4 is 9, and then when you plug in 0, you get 0. So 9. Is that the same thing you get when you do 1/2 base times height? 1/2 3 times 6 is 9. Yeah. So I know it seems like kind of crazy to do this problem this way when you can just use 1/2 base times height. But the idea is we're using it on something that we can verify to start, so that when we move on to irregular shapes that don't have a formula, we can use this same technique. So the idea, slice up your object into little rectangles, add them all up. When you add up an infinite number of rectangles, it becomes an integral. So here's the general procedure. Okay. Draw a typical slice, label your diagram. So that was the x, the delta x, the h, right? Write the area or the volume, if you're trying to find a volume, of one slice. And make sure that formula has only one letter in it, right? Only x's, not x's and h's. Write the sum of all the areas or volumes of n slices using sigma notation. Write the actual area as a limit as n goes to infinity, and then change that to a definite integral. Calculate the value of the integral using antiderivatives, or your calculator if you can't use antiderivatives. All right, let's do another one. So I want to find the area of this circle. It's got radius 3. We all know the area of a circle is pi r squared, right? So I will be able to verify my answer when I'm done by checking, is it 9 pi? But I'm going to do it by slicing to get an idea of this technique. So I have already drawn a typical slice. Just picked a slice of my circle, and I'm going to slice it, slice it, slice it, slice it, and then add up the areas of all those slices. And each of these slices is almost a rectangle. And it's got width delta h, and then I need to know its height. So how could I figure out the length of this thing? Right, if I'm going to do length times width, width is delta h, how could I figure out its length? I can use the diameter somehow, yeah. So, but is this a diameter? Is that 6? Right. Okay. Nice. Right. So I can draw a radius wherever I want. It's always going to have length 3 in this case. So can I use that to get the width of my triangle? So that vertical piece I just drew, it's h, right? So I have a right triangle now. Hypotenuse 3, height h. Can I get its base? Yeah, just use the Pythagorean theorem. It would be 9 minus h squared radical. And that is half of that rectangle, the base of that rectangle. So this whole base would be radical 2 radical 9 minus h squared. So the area of my slice is going to be delta h, the width of the rectangle, times the length of the rectangle, which is 2 radical 9 minus h squared. Then I'm going to add up all my slices. So I'm going to take a sum, 2 times radical 9 minus h sub I squared times delta h. Let I go from 1 to n. And when I take a limit as n goes to infinity, this is going to become an integral. So this is going to be the integral of 2 radical 9 minus h squared dh. And then what should I use as my bounds of integration? H is going to go from what to what? 0 to 3. Yeah. And when I find that integral, what's it going to tell me? Close. It's going to be half the area. Because if I start at 0 and go to 3, I'm just getting that much. Right? So I should double it to get the area of my circle. All right, so I'm just going to have my calculator do this integral. And then once I have the calculator evaluate the integral, I can compare it to the formula of just using pi r squared and see if this works. All right, so I'm going to do 4 times, I'm pulling that 2 out, so I get 4 times, the integral of the square root of 9 minus x squared, comma x, comma 0, comma 3. All right, 28.27, let's compare that to 9 pi. 28.27, so same thing. So again, why would I do this? Because eventually, someday, I'm going to use this technique on irregular shapes that don't have a nice, easy formula. So we start on things that we are able to verify that the technique works. All right, I used a little bit more room than I meant to. Okay, one more together for area. So here's a more irregular shape, right? So I want to find the area of this shape. It's drawn in the xy plane, and it's the area sort of bounded by the line 3x plus y equals 6, and the curve y equals x squared minus 4, and the y-axis. So I'm going to do it by slicing. I could think of it as areas under curves and break it into different integrals and add them up, but I'm going to do this by slicing. All right, so moving along the x-axis. So here's 0, and I'm going to draw a representative slice, which looks almost like a rectangle, at a value of x. At some random x value, I'm going to draw a rectangle. And its width is delta x. And what would the height of that rectangle be? Yeah, so it's going to be the distance between 3x plus y equals 6, between that line, and the curve y equals x squared minus 4. Okay, so let's see. This is going to be better if I just rewrite this as y equals 6 minus 3x. So that way I have a y coordinate, right? So I've got this height here is a function of x. It's 6 minus 3x. And this height is x squared minus 4. So the distance between them, I would just subtract, right? To find the distance between two values on a number line, you subtract them. And I will take an absolute value, right? I would normally I could do the bigger one minus the smaller one, but I could also do the smaller one minus the bigger one if I just do absolute values. So if you're unsure which one's bigger, just use absolute value. Okay, so the area of my slice is going to be delta x, right? That's the width, times the height of my slice. And the height of that slice is going to be 6 minus 3x minus x squared minus 4. Yes. Wouldn't it be plus? That's a good question. So let's look at numbers instead of formulas. So let's say I want to find distance from 8 to negative 10. Right. You would do 8 plus 10, right? So you took the absolute value of this guy first. Or I could do 8 minus negative 10. That makes sense? So that's why it was that's where the subtraction comes from. If you're going to use the actual number and not start playing with absolute values, you do a subtraction. Does that make sense? Nope. Or, right, I could have written 8 plus also 18. It's just, I don't know, preference, I guess. You still subtract. Yeah, right, look. So instead I put a 2 here. What's the distance between 8 and 2? 8 minus 2, 6, right? And the distance between two values on a number line, you subtract. Okay, so the area of my slice ends up being, I should combine these first and then do times the delta x. Negative x squared minus 3x, and then I have 6 minus negative 4 plus 10 delta x. Then I just have to add up all of these slices from where to where. How do you know 2? How do you know that that's 2? Yeah, the two functions meet at their 0, so you could set them equal to each other and solve, or you could say, oh, well, that's the x-intercept of both. You could set each one of them to 0 and solve. So but it's clearly drawn on the positive side, so 2 is the value I'm going to. So I'm going to have all these little rectangles. I'm going to add them up. I have n of them, and then I let n go to infinity. So the area of my region is going to be a sum of all rectangles that look like this. Have an area like this, each one using a different x value, which you could call xi. So this would be negative xi squared minus 3xi plus 10 delta x. And then we let n go to infinity. So it's approximately that. And then the area of my region is exactly equal to what happens when I let n go to infinity, which gives me an integral from 0 to 2 of negative x squared minus 3xi plus 10 dx. Delta x becomes dx. Oops, didn't mean to put the I there. All right, so then we calculate this area. Plug in a 2 and I get negative 8/3. 2 squared is 4 times 3 is 12 minus 6 plus 20. And then when I plug in a 0, I get 0. The what? Oh, the bounds on my integral? So I am stacking up all these little rectangles, right? And I'm going to draw my first one at x equals 0, right? And then I'm going to keep drawing them until I get here, which is 2. Right? And the reason I know that is 2 is because I can set this function equal to this function and see where they cross. Okay, so negative 6 plus, I'm not going to do this in my head. Okay, 14 minus 8/3. 34/3. And this one we could verify using two other integrals, right? I could integrate under this line 0 to 2, and then take the absolute value of the integral 0 to 2 of x squared minus 4, add them together. So I could verify it if I wanted. Does this procedure kind of make sense? All right, let's use this same idea to find a volume, and then I'll let you try some. Okay, so I have this solid. It's got a rectangular base. It's like 14 meters by 10 meters rectangular base, and then I have parabolic looking things as the roof. The roof kind of looks parabolic, and it's got a height of 7 meters. All right, so we're going to set up the integral, and then we'll just use a calculator to evaluate it. Now, this kind of shape is not something that we have a formula for to find the volume of this kind of thing. So we don't have any way to verify this when we're done. But it's kind of set up already where I'm going to slice it, and you can see I've drawn a typical slice right here. And that typical slice, what is its shape? Approximately. A rectangular prism, right? It's like a box, yeah. So my typical slice is a box. So I have to find the volume of my slice. Right, so I'm just going to look at this one slice and try to find the volume of that. And then I'll add up all my volumes, the volumes of each slice. Okay, so taking a look at this slice, its width is delta y. So remember, the volume of a slice is length times width times height, right? Call the height delta y. And then we've got to find its length and its width. And it has to be in terms of y, right? Because delta y is my height, so I have to only use one variable to describe this whole thing to be able to integrate. So I need to know that length and that length. True. 10 doesn't change. These are all 10s, right? So we can call that the width, say. Good. All right, so then mystery is this distance. Yeah, yeah. So hopefully this isn't actually parabolic and it's semicircular. Yeah. If we assume that this is a semicircle, and that looks reasonable, then we could say if you drop a that's y, and if that's 7, then so is this, if it's a semicircle. And I didn't draw that really perpendicular. So it would be the square root of 49 minus y squared. Y times 2. Oh, yes, yes, I just got this piece, yeah. So yeah, we got to double it to make the whole length. Thank you. All right, so that's the volume of my slice. That cool? Make sense? All right, so now I got to add up all of my slices. So I'm going to sum 2 times the square root of 49 minus y sub I squared. So each y value we'll call y sub I. times 10 times delta y. And this is the volume of my region approximated, right? Using n slices to approximate it. To get the exact volume of my region, I let n go to infinity, which will give me an integral. So this is going to be an integral. 2 times 10 is 20. Delta y becomes dy. And then what should I use for my bounds on y? I'm going to be stacking up these rectangular boxes from what value of y to what value of y. 0 to 7. We'll start down here at the base of my thing where y has a height of 0, and then y is going to go up to 7 meters. So 0 to 7. All right, so then we'll use the calculator to get the value of this thing. Okay, so 20 times the integral of square root of 49 minus x squared, comma x, comma 0, comma 7. $769.69. There is, you're right, yeah. Yeah, because this is, sorry, this is a cylinder, right? It's the top half of a cylinder. And the area of a cylinder would be pi r squared h. So pi times the radius is 7, right? 7 squared times the height, which is 10. And divide by 2 because it's just the top half. 49 pi times 10 over 2. 769.69. So if you ever wondered how we know these formulas for the area of a circle, the area of a cylinder, area of a triangle, this is how we discover those things. Integration. Okay, your turn. Use some slicing to find areas and volumes.